Hello, in this video we're going to examine the radial properties of hydrogenic orbitals. Now what does that mean? Well, radial refers to properties that depend on the distance of an electron from the nucleus. Hydrogenic means hydrogen-like, and by hydrogen-like what we're talking about are one-electron systems, systems which consist of a nucleus and an electron, two particles only. So that means that this would apply to hydrogen, of course. It would also apply to helium plus. It would apply to lithium 2 plus. These are systems which have a nucleus and but one electron. So the radial component of the wave function, the component depends on distance r, and doesn't depend on the angles theta and phi in the spherical polar coordinate system, is what we're going to be looking at here. The total wave function, of course, depends on all three of those variables, but again, we're just looking at the dependence on the distance r. So we have a list here which shows the radial component for several orbitals from the 1s orbital to the 3d orbital. The radial component depends on both the n quantum number and the L quantum number. So the 1s orbital corresponds to n equal 1, L equal to 0, and of course all s orbitals correspond to L equal to 0. So here we have the 1s orbital, the 2s orbital, and of course you can see as we get to higher principal quantum numbers, 2 is a little bit more complex than 1. And of course we get down here to 3D, which corresponds to n equal 3 and L equal to 2, and this is the set of orbitals corresponding to all of that. These are the radial components. I also have listed here a table which may also be found in a Word document that's posted on the class website that indicates, again, the orbitals, the radial component, and how you would enter that radial component in Wolfram alpha. So that's something that you can use when entering these in Wolfram alpha. You can also use it in the Wolfram cloud. All right, so let's take a look at some of these orbitals and the radial components. So here we have some plots which show the probability density associated with the radial component, and that means we're just squaring the radial component because all of these components are real that we're looking at. Here we have it for s orbitals, the 1s, the 2s, and the 3s. And you can see that all three rise to a maximum, although it's not shown here because it's not carried out to r equals 0, that they reach a maximum at r equals 0, which of course corresponds to the nucleus, which should cause you to ask some questions, I would hope, and we'll come back to this in a few minutes. Here is the corresponding plot for p orbitals, again the radial component squared, and we see for the p orbitals the value is 0 at the nucleus. We'd also see the same for d orbitals if we were to plot those. Now, if you want to plot these in Wolfram alpha or in the Wolfram cloud, it's actually pretty simple as long as you have the correct functional form. So here's the equation, and we're looking at just hydrogen here, so the z is equal to 1 as noted earlier for this. So this is hydrogen. The A corresponding to the Bohr radius has to be entered in order to plot it, and that's equal to 52.9 picometers. So the scaling here is going to be in picometers. So here's our radial component of our wave function squared from r equals 0 to 500 picometers. And it's just a very simple exponential as seen above. But again, this is how you would enter that. If we took this and entered it into the browser in Wolfram alpha, we will get this plot, or we could do it through the Wolfram cloud by entering it with the freeform method. Now, the question that we were talking about earlier, which I said should be of concern to you, is the fact that it reaches a maximum at the nucleus. And that should not make any sense because we have this basic intuition that the electron does not exist at the nucleus. It's not going to be at the nucleus. So why should that probability density be a maximum at the nucleus? You know, we could say there's no crying in baseball and there are no electrons at the nucleus. So what's going on with that? Well, so we're only asking the wrong question when we ask about the maximum probability density, because that is actually a calculation of the density at a particular point in space. The more appropriate question to ask is, what's the probability of finding an electron at a particular distance from the nucleus? Now, you may think, well, how is that different? It is if you think about a sphere and the surface area of a sphere. As we increase r, you know the surface area increases. As the distance increases, it goes as r squared. The surface area of a sphere is 4 pi r squared. So if you think about calculating probability densities, if we calculate the probability density at a particular value of r, we're just calculating the probability of an electron being at a particular point on the surface of that sphere. Well, that's not the entire surface area of the sphere. And so we have to take that into account if we're asking the question about what's the probability of finding it at a particular distance, not a particular point. To do that, we use something called the radial distribution function. And that radial distribution function shown here is just very simply r squared, the distance from the nucleus squared, times the radial component squared. Now, if we plot this radial distribution function, we're going to see for the 1s orbitals along the top row here this behavior, where one thing we'll note is that we've got local maxima for the 2s and the 3s orbitals, that the 3s has 3 local maxima. All right, the 2s has 2 maxima, one of which is a global, and I should mention for the 3s we have 3 maxima, but we've got the global maximum here, which is out over here somewhere in the 600 to 700 nanometer picometer range. Notice the horizontal axis is in picometers. For the 2s orbital, it's less than 300 picometers, and for the 1s orbital, it's less than 100 picometers. So we can certainly see, first of all, our general notion that the electron on average distance, the average distance, should increase as the principal quantum number increases in this situation. All right. We also notice, importantly here, is that the radial distribution function has a value of 0 when r is equal to 0, so it is 0 at the nucleus. The 2p orbital, 3p, 4p in the second row, this is the behavior that we see for each of these as a function of distance from the nucleus. And here we have the bottom row, we have the d orbitals, 3d, 4d, 5d. And again, notice the difference in the distances. The 5d orbital we're carrying out to 3,000 picometers, so we're seeing that distance increase as we go through this. All right, so that's how the radial distribution function works. Now let's ask the question about determining the probability of finding an electron within a particular region of space at a particular distance from the nucleus. And here we just use our integral. If we're interested in finding what the probability is of finding the electron between a distance of a and a distance of b, then we're going to take our radial component squared. We're going to multiply it by r squared dr. So we're just doing the integration, the limits of integration between a and b. It is important to note that we must include this r squared in our integration when we're doing this. And the probabilities that we've used with Cartesian coordinates, we've just taken the wave function, squared it, and multiplied it by the appropriate volume element. In this case, with spherical polar coordinates, we have to multiply it by r squared times dr. So that's how we do it. So let's ask, all right, what's the probability of finding an electron in the 1s orbital between 0 and 100 picometers from the nucleus? So we're going to go ahead and enter that. Again, here's a Wolfram alpha free-form language integration that we're going to use. So here is the radial component right here, ranging from this 2 to the end of the parentheses for the exponential term. We square our radial component, then we multiply it by r squared, and we're integrating it from 0 to 100. That's going to give us a probability of finding it between 0 and 100. we have entered, notice, the A or the Bohr radius here at 52.9 picometers. So we are integrating with respect to picometers. So we perform that integration, we find that it's 0.727975, or roughly 0.73. So there's a 73% chance that a 1s electron in the hydrogen atom will actually be found between between the nucleus and 100 picometers from the nucleus. One could reasonably ask, of course, is how would this be different for helium plus? So I would challenge you to go ahead and enter this for helium plus. How would it be different? How would the entry be different? And see what you get. What do you think you'll get? Now what about average distance? How can we calculate the average distance? Since the radial distribution function gives us a probability associated with distances from the nucleus, how would we approach the problem to calculate the average distance? Well, remember averages in quantum mechanics, we use expectation values, and the general expression for expectation values for something that we observe, represented by O, here's our expectation value, is this particular integral here. So now, with regard to this, since we're talking about the radial distribution function, so here's the equation. I've actually corrected it to indicate that we're using the radial component as opposed to the full wave function. So the radial component, all right, times the result of the operator, and the operator corresponding to the particular observable, what we're measuring, operating on the radial component. And again, the r squared dr, that r squared is always going to be there when we're doing integrations with respect to the radial distance from the nucleus. And so we've got this integral that we're evaluating. And in this case, if we're talking about average distance, what we need to know is what's the operator corresponding to distance. And the operator for distance is just very simply multiplication by r. So all we're going to do here is we're going to replace the operator with r, meaning we're going to multiply everything by an additional r value within this integral. So I'm going to leave that up to you, and you would enter it into a particular cell or enter it into Wolfram alpha to do that calculation where the operator is multiplication by r to determine the average distance from the nucleus. What about the most probable distance from the nucleus? So if we look at the radial distribution function plots again, the most probable distance, of course, is going to be at the maxima here in these radial distribution functions. So we can really estimate what the most probable distance might be by just simply looking at the plot. Right, so we know that is going to give us an estimate. It's not going to give us an exact value, but it's going to allow us to get a ballpark figure, even smaller than a ballpark figure, a pretty close value for the average, for the most probable distance. So going back down here, then how do we get the most probable distance? The first question that we have to ask is, with our radial distribution function, as we looked at the plots above, how do you find a function maximum? And this is a question I'm going to leave to you. All right, I want to find the maximum of the function. How does that relate to the derivatives of the function? So what must I do here to find the maximum for the function, given that the radial distribution function is r squared times the radial component squared? All right, we can do this with a hydrogen 1s electron by remembering what the radial component is for the 1s electron. So the real key to solving this problem is, how do I determine a function maximum? How do I use derivatives to determine a function maximum? You can do this in Wolfram alpha, all right, or the Wolfram cloud. You may find it's easier to do it in multiple steps rather than all at once. But I'm going to leave that as a mystery for now, so you could try to figure this out for yourself. We'll come back to this later when you've had a chance to work on it and see if you can come up with an answer. As you go through this and you calculate the most probable distance, compare it to the average distance, and also ask yourself if, given the radial distribution functions shown here, and since we're dealing with 1s orbital, we're talking about this one, given the radial distribution function, does that value make sense? We'll stop here and we'll come back with more on this later. Good luck.